At its core, optimization is about finding the best possible choice from a set of alternatives. But what does best really mean? In mathematics, it usually means minimizing or maximizing a function. Sometimes this is straightforward. A smooth, well-behaved function gently curves towards a single minimum, making the solution obvious. Now, let's consider a function. Something like f of x equals x squared, which forms a nice U-shaped curve. Here, minimizing the function is easy. Just go to the lowest point, which is at x equals 0. Now, let's add a variable. Suppose we have the function f of x equals x1 squared plus x2 squared. This time, the function forms a curved surface, but the idea remains the same. If we dropped a marble on its surface, it would roll down to the lowest point. That's how we can intuitively think about minimizing a function. But what if we add constraints, like y minus x equals 2? We have to stay inside a certain region. And if the function itself is complicated, things can get even harder. When we move beyond convex functions, finding the true minimum can be incredibly challenging, because we can get stuck in local minima. And so, when we aim to minimize a polynomial, a natural idea is to find the greatest lambda such that said polynomial minus lambda remains non-negative everywhere. In other words, we want to find the greatest lambda for which the polynomial always stays above the plane y equals lambda. Think of this as a horizontal plane moving upward until it touches the lowest point of p of x. At this point, p of x minus lambda becomes a polynomial that is always non-negative. At first glance, finding this lambda might seem simple, but in reality, determining whether a polynomial is always non-negative and thus computing this optimal lambda is an extremely difficult problem. In fact, it is an NP hard, meaning there is no known efficient algorithm to solve this in the general case. Fortunately, there is a special case where this problem becomes much easier. If p of x minus lambda can be written as a sum of squares of polynomials. If we can express p of x minus lambda as q1 of x squared plus q2 of x squared, etc., then we immediately know that p of x minus lambda is always non-negative, since each term is a square. Unfortunately, not every polynomial that is positive is necessarily a sum of squares. That might sound surprising at first, because sum of squares polynomials are always non-negative. Here's a famous example, the Mochkin polynomial. This polynomial is given by this formula, and is always positive, but it is not a sum of squares of other polynomials. If not all positive polynomials are sum of squares, does that mean the sum of squares methods are useless for optimization? No. This is where the Archimedean property comes in. A set of constraints is Archimedean if there exists some large number n such that n minus x1 squared x2 squared belongs to the quadratic module generated by the constraints of the problem. Intuitively, this means that our problem is bounded, preventing extreme behavior at infinity. But if the Archimedean property holds, we can approximate any non-negative polynomial arbitrarily while using sum of squares. To make this a little more rigorous, we introduce the concept of quadratic module. Given a set of constrained polynomials, we define the quadratic module generated by these constraints as follows. What does this mean? It means that instead of checking whether a polynomial is a direct sum of squares, we check if it can be expressed as a sum of squares plus weighted constraint functions. This is super helpful because many constrained polynomial optimization problems naturally fit within this framework. A fundamental result that makes this precise is put in our positive Stellensatz. It states that if a polynomial is strictly positive over a compact set, then it can always be written as a sum of squares plus constraints, meaning it belongs to the quadratic module. In practical terms, this is what allows us to use semi-definite programming to solve polynomial optimization problems. Even if a polynomial is not exactly SOS, we can still use SOS-based relaxations to approximate the true solution. Now polynomials have something we call a quadratic form. Let us introduce the vector z of monomials. Here we have an example with two variables. Each polynomial can be written as follows. with Q a symmetric matrix? It just appears that for positive polynomials, the matrix Q is positive semi-definite, which means its eigenvalues are all positive. We've talked about semi-definite programming without giving it a proper introduction. SDP, as we'll call it, is a type of convex optimization problem where the objective is to optimize a linear function over the space of positive semi-definite matrices, which is very fitting for our problematic. Let's come back to our original problem. To better visualize how this all comes together, we'll use a practical example. Our goal here is still to maximize lambda. But as we mentioned earlier, directly ensuring non-negativity is computationally hard. Instead, we'd like to reformulate the problem by relaxing the constraint into a simpler convex form. The relaxation involves expressing p of x minus lambda as a combination of SOS polynomials and the constraint functions. This is called the SOS relaxation. And so we notice that our set of constraints is Archimedean using n equals 1, and our function f is a positive polynomial. Thus by Polynomial, we can apply what we have been setting up until now, that p of x minus lambda is inside the quadratic module of the constraints. And to make the problem computationally feasible, we use a degree truncated version of the quadratic module, that we denote mt of g, limiting the SOS polynomial's degree. This simplifies the problem while maintaining accuracy as t increases. This allows us to define a proper SDP for our function. And using the quadratic form we saw earlier, we can decompose the sigma i's into products of monomial vectors and positive semi-definite matrices. By cleverly rewriting the formulas using what we know, like the quadratic forms of the sigmas, we arrive at a version of the problem that is solvable using a conventional SDP solver. Computing the first relaxation for this problem by restricting the degree of sigma 0 to 4 and the sigma i's to 2 gives us a certain lower bound for lambda. As we move to higher order relaxations, the polynomial becomes more accurately approximated. Each subsequent relaxation refines the lower bound and corresponds to a higher degree in the polynomial semi-squares decomposition, and the solution becomes increasingly precise. However, this improvement does not continue indefinitely. At some point, the solution plateaus. Here, we computed in MATLAB the second relaxation, and it gives us a way higher lower bound for lambda. It is very similar for the third relaxation, but we see that the solution tends to get closer to 0 as the relaxations increase. And so we started with an NP-hard problem, but through the clever use of polynomial properties, semi-definite programming, and some mathematical ingenuity, we've developed a practical method to approximate its optimal solution efficiently. This approach not only showcases the power of optimization theory, but also opens doors to tackling complex real-world problems with relative ease. A special thanks to Jean-Bernard Lasserre, who is one of the brilliant minds behind this optimization technique, and to Clément Royer, who has been the best optimization teacher this semester, and without whom this video wouldn't exist.